questions, and if and when you run out of questions, I have a couple of problems we can work on. But that's sort of all it's come down to. Anybody have any questions or problems you'd like me to work?
Something from Friday.
What?
Something from Friday.
From last Friday? Yeah. A column buckling problem? Okay. Yes. Yes. So I think what I'm going to do on column buckling is you're not going to have to derive anything. I'm just going to give you the formulas for pinned ends and the formula for clamped ends, and then you just have to use the formula. So it should be really easy, but you have to know how to do it. So okay, let's do this one. So it's pinned at the bottom. It's pinned at the top, which also you can think of that as like pinned at the top just means that it's constrained to move vertically at the top. It can't bend over. It's like you could think of it as like so that's where the sort of pinned idea comes from. It's free to rotate at the top and it's free to rotate at the bottom. And let's say that it's 3 meters long. And there are also supports in the middle. It has a rectangular cross section. So the cross section looks like this. The long dimension, which is going from left to right on the page here, is 0.06 meters, 6 centimeters. And the thickness going into the page is 2 centimeters, 0.02 meters. The Young's modulus is 100 times 10 to the 9. And we want to figure out first what's P critical, and second, what's the elongation? At P critical. Well, this can be, it's definitely a lot more, it takes a lot more thought if you have to derive the formula, but I'm just going to give you these formulas. So P critical for pinned, so pin joints on both sides, is E, wow. Something big's going down. EI n squared pi squared over L squared. And that's for n equals 1, 2, 3. Okay, and those solutions, so this is n equals 1 corresponds to a solution like this. It could go to the other side too. N equals 2 corresponds to a solution like this. Which one of those do we want in this case? 2, yep. So we want n equals 2. So P critical is equal to, so 4EI pi squared over L squared.
When you say pin,
Yeah,
balance pin on the right.
yeah, and these are both equivalent. Even though there's no pin here, the pinned at the top just means that the angle is free to take whatever value works out. As opposed to clamped, anytime the top is clamped, the angle is not free. So no matter what happens when the top is clamped, it has to be vertical at the top point. At this point, it could be 20 degrees or whatever. It won't be that big, but it can change. Okay, so I. In this 2D problem, how do we calculate this I? So you have to be able to do that. Because remember, I has one dimension that's to the first power and one dimension to the third power. So it's really important that you choose the right one.
Is the one the third the longer one?
Yeah, in this case, I mean, since all our motion that we're interested in is happening in the plane of the page, so it's going to be, when it bends, it's going to bend like this, you know? And so the value that you take to the third power is the one like in the direction of the deflection. Okay? So like imagine this, turn this sideways and imagine it being a beam that's in bending. And just think about which one of these would be your H and which one would be your B.
So the third would be the, suppose, 0.06.
Yeah.
So, 0.02 won't change at all. Or, I don't know.
No. No, we're not going to assume that anything changes. In fact, that's kind of, I think that's totally generally true in this class, that we always assume that the deformations are small enough that we can use all our initial values for measurements through the whole calculation.
So if that were not, if it were opposite,
Yeah.
would you just not be able to calculate I, or?
No, if it was, like if I had switched it with if I had made it so that the 0.2 was representing this thickness and the 0.6 was going into the page,
Right.
then it would be 1/12 times 0.06 times 0.02 cubed.
Okay.
So it would be a lot easier to bend if it was oriented the other way.
How did you word it one more time? Which one you raised to the third power? The one.
Well, remember that when we just think of beam bending. So if we have,
I guess.
okay, so here's like a beam bending problem. So the problems we do, they're bending along one axis, okay? And that H is, I guess you could say it's perpendicular to the neutral axis of the bend. Or it's in the plane that all the forces, it's in the plane of the shear forces. It's in the direction, it's parallel to the shear force that's making it bend. Okay. All right, so anybody else have questions about that? If, because, you know, like in a problem like this, if you use the wrong value for B or H, you could be off by a huge factor, you know.
So is there a chance, like in reality, that it would bend, it would buckle the other, like out of the page?
Yeah, I mean, this, if you're doing an,
Before it buckled the other way?
yes, so if you're doing an analysis like this, you need to know for some reason that the plane that you're looking at is the plane where you're worried about buckling. So, I mean, maybe it's supported along the whole side or something, and that's why we're only worried about this plane or something like that. But if that was, yeah, I mean, if there was nothing else going on except what I drew, then there's no way it would buckle in the plane that we've drawn because it's weaker to bending out of the plane, and it doesn't have any supports at the center, you know.
But also that, like the angle at the both ends would not be free to rotate then, based on
That's
the
true.
skin joint.
Yep, you're right about that. But so all of these, we're just assuming we know what plane we're worried about, and that's all we're taking into account. Okay, so let me draw this. So there's the H, there's the B. So I is equal to 1/12 times 0.02 times 0.06 cubed. What do you get for that?
2.6 -7.
Okay. And so P critical is equal to 4 times 100 times 10 to the 9th times 3.6 times 10 to the minus 7 times pi squared divided by 3 squared. And what do you get for all that?
157,914.
Ooh, that's half pi. How did that come out? What is it?
157,914.
157,914. That's a big force.
Divided by 9 times 3.6.
Okay, so that's P critical. Anyone have any questions about that? So now for part B, we're imagining a beam that's under a load of 157,914. It's compressive. And we want to use the elongation formula to calculate. In this case, it's going to be shortening. Okay, so first we have to calculate the internal loads. It's pretty simple here. It's just in compression, so it's going to be a negative value. It's going to be a value of negative 157,914. So Newton's second law, well, you have to do the cut first. So 157,914, the internal tension over here. And so Newton's second law says T is equal to negative 157, 914. And then the elongation is equal to the tension times the length over EA. So we have negative 157, 914 times 3 over 100 times 10 to the 9th. And then the area is 0.0012. Yeah, that's got to be it. So what do you get for the elongation?
-0.0039.
Meters. So 3.9 millimeters. Yep, shortened by 3.9 millimeters.
For the buckling, when we're doing, is P the same thing as T?
Yeah. I mean, P is just the name, yes. P is just the name of the compressive load. I mean, it's not really the same thing as T. T is the internal load, and P is the external load.
We're using P as T when calculating the.
Well, yeah, because the external loads are pretty simple, the internal loads end up being the same as the external loads. But I mean, really, these values are the P values. This is P, and then we did a cut to calculate T. But it was a simple case, so T just ended up being negative P.
So is there some relationship there then?
I mean, I guess in all the problems we're doing, they're going to be the same, but you should keep in mind that what you're using for elongation and for all of those macroscopic deformations are the internal loads. And what we're using for the buckling equation are external loads. Any other questions about that one?
And P critical is the amount of force, like the most you need to get it to start to deform.
Yeah, the least you need, the minimum when it starts to be in danger of buckling.
So is 3.9 millimeters like the smallest amount that it'll buckle?
Isn't it the most that you can actually?
At the point where you are concerned about buckling, that's how much it's going to shorten. They're kind of unrelated questions.
But that's like P critical is like the smallest amount of force it's going to take to like and then
To wreck it.
deform it.
Yep.
So
And so is that the smallest amount that it would deform? Like if you had more force, would it deform more?
Well, that elongation formula assumes that it keeps the same shape. Buckling means that it would sort of collapse, you know. So once it buckles, you don't know. I mean, it's gonna just crush down. But if you assume that critical point, or imagine just a little bit less than that critical value, before the sides bulge out and it collapses, that's how much it's going to compress down as a straight column. So before it buckles, that's how much lower the top is than it was without load. Any other questions? Okay. So now let's do a combined statically indeterminate problem with a couple of things going on. So let's say that this beam is between two fixed supports. It has a length of 4 meters. And a quarter of the way along its length, there's a 5,000 Newton force. Let's say the coefficient of thermal expansion is 1.0 times 10 to the minus 5. And the Young's modulus is 100 times 10 to the 9th. And here's a cross section. So let's say it's 10 centimeters tall and 2 centimeters wide. And let's say that in addition to this, this load from above, the temperature increases 80 degrees Celsius. So what are the reactions? All right, so what's the first step? The first step is just do the statics. See what you can get from isolating the whole thing, and then we'll go from there. You know, this is the way that in a complicated problem you would identify whether it's statically indeterminate or not. You might be able to just, you know, you look at this complicated thing. As far as you know, you might be able to solve it right off the bat and never go into that stuff. So free body diagram of the whole beam. We have the 5,000 here. We're neglecting the weight. What are the reactions at the ends? But so yeah, like what type of loads do those apply? Yeah, those are fixed joints. We don't know anything about the couples that are going to happen.
Well, if the 5 is on the middle, though, can we like cancel out some of those?
Well,
Is that what we did before?
I don't think we've ever done that as like a strategy, but it's true that a lot of stuff would cancel out. But I don't know. I feel more comfortable just solving. It doesn't, you know, just do the calculation and see, you know, like you think like, okay, well, I think it's going to be, these are going to be the same. Might as well calculate it and then feel good at the end when you're right. And then if you're wrong, feel really good that you did it, you know. Okay, so let's call this the force RA. This is the force RB. Oh, yeah, and we are going to need those. So MA and MB. So Newton's second law says RAX, RAY plus 0, negative 5,000, plus RBX, RBY is equal to 0. And the moment equation, I'll use A as the about point. So we have MA minus 1 times 5,000 plus MB plus 4 times RBY equals 0. So the first equation says RAX plus RBX equals 0. The second equation says RAY plus RBY is equal to 5,000. And the third equation says 4RBY plus MA plus MB is equal to 5,000. So we have three equations, 1, 2, 3, 4, 5, 6 variables. That's the RA vector, the RB vector, MA, and MB. Okay, so now there are two things going on. There's a deflection thing and an elongation thing. The elongation the total elongation of the beam has to be equal to 0 over its whole length, and the total deflection over the length of the beam has to be equal to 0. And those two things are totally independent of each other. So we can just break it up, do the elongation part, be done with that, and then do the deflection part separately. So let's do elongation first. So the only elongation that we have is due to temperature change. And that's equal to, well, okay, so that's kind of not accurate. So basically what's happening is the increase in temperature is going to make the thing want to grow. It's going to make it want to expand. And so because the two ends can't go anywhere, the two ends have to apply a force to compress it so that the temperature, the elongation due to the temperature change plus the elongation due to the external loads at the walls add up to 0. They have to counteract each other. Okay. So let's first do the temperature one. The coefficient of thermal expansion is 1 times 10 to the minus 5. The length of the beam is 4. And the increase in temperature was 80. So what do you get for that? And that's in meters. And now we can do a cut. Well, actually, let's see. We're going to have to do 2 cuts. So cut 1. So if we're going to calculate the elongation that's caused by these external loads, well, so we could do 2 cuts here because there's an external load, but that external load doesn't have any horizontal component, so it's not going to change anything about the horizontal motion. But if you want to, if you see you see a point force there, and you want to do a separate cut on the left side and a separate cut on the right side, it'll work fine. But we'll get the same thing if we just do a single cut. Does that make sense? Or So, yeah, the vertical stuff and the horizontal stuff are just totally independent of each other. So since we're doing horizontal calculations right now, that 5,000 might as well not even be there. It doesn't affect anything. So we can just treat it like that 5,000 isn't there and just do a single cut because there's no horizontal point forces. Or we could just right now calculate all the internal loads. I don't know, maybe we should do that. So x between 0 and 1 meter. What are the loads applied to that first cut on the left? Yeah, we have the, so we have that, we have the couple, and then we have the internal loads, T, V, and M. So Newton's second law says RAX, RAY plus T negative V is equal to zeros. So T is equal to negative RAX. V is equal to positive RAY. And then the moment equation, MA plus M, the bending moment, minus Vx is equal to 0. So M is equal to negative MA plus Vx. So that's equal to RAY times X minus MA. And now the second cut, that's valid for X values between 1 meter and 4 meters. So on this one we have the force RA, the couple MA, and now we also have that downward 5,000 Newton force, and then the internal loads.
Does RAY do anything? Because X is 0 at the left for the first cut.
Will what do anything?
Because X is 0 at the left.
Mm-hmm.
Is it? Do we?
For this, for the moment function?
Uh-huh.
Well, X is, that first cut is all the points up to 1.
So 1, okay.
So it'll be 0 at the end, but not over the whole thing. So Newton's second law says RAX, RAY plus 0, negative 5,000 plus T negative V is 0. So T is equal to negative RAX, and V is equal to RAY minus 5,000. And then the moment equation, MA minus 5,000 plus M minus Vx equals 0. So M is equal to negative MA plus 5,000 plus Vx, and that is RAYX minus 5,000x plus 5,000 minus MA. Since the internal tension, so this is what I was saying before I started doing this internal loads calculation. If you look at the internal tension, it doesn't change anywhere along the beam. It's just equal to negative RAX the whole way. So we can just do this as a single, we don't have to break it up into two pieces. Both pieces are going to work exactly the same. So our elongation due to tension is equal to TL over EA. And so that's equal to negative RAX times the length is equal to 4. E is 100 times 10 to the 9. The area is 0.002. And so can someone calculate those numbers, get a coefficient for that? Okay, times RAX. And so then the total elongation equation says the total elongation is equal to the elongation due to the temp change plus the elongation due to tension for tension, what do we get there? 0.0032. So 0.0032 minus 2.0 times 10 to the minus 8 RAX is equal to 0. So RAX is equal to, what do you get, 0.0032 divided by 2.0 times 10 to the minus 8? 1.6 times 10 to the 5th? Okay, newtons. And so now we can go back, plug that into equation, I think it was 1. And so our BX is just the opposite of that. So our BX is equal to negative 1.6 times 10 to the 5th newtons. Okay, so what directions are the external loads? Are they this way or this way? No, in. Because this is the one on the left is pointing in the positive x direction. So and it makes sense. Like if you think about what's happening, you should be able to, on these kind of problems, you should be able to like make physical sense out of it. The temperature is making it try to grow. It's running into the walls, which is keeping it from growing, and so that has to be a compressive force that's keeping it from growing like it wants to. Okay. All right, so now we're going into the hard part. So now we have to go to the deflection. And here's what we know. We know at x equals 0, first of all, the deflection is equal to 0, because that can't go anywhere. Second, because of the fixed joint, the angle can't change. So V prime has to be equal to 0. Those are always both true at any fixed joint. And so the same two have to hold at x equals 4. So first of all, the deflection has to be equal to 0, and second, V prime has to be equal to 0. All right, so our deflection equation says V double prime is equal to 1 over EI times the moment equation. And we're going to have to break this up into two pieces because our moment function is different for cut 1 and for cut 2. So okay, so for cut 1, this is the one that's valid for x values between 0 and 1. What was our moment function? Okay. R A Y X minus MA. So integrate that once, and you get V prime is equal to 1 over EI times the quantity RAY over 2 x squared minus MAX. And then you have a constant of integration, C1. And now integrate that again. And you get that V is equal to 1 over EI times RAY over 6 times x to the third minus MAX squared over 2 plus C1x plus C2. Okay, we can try to solve for those constants using what we know about the end conditions. Let's see, so at x equals 0, so this is just the first cut, so we can't do anything with the end conditions when x is equal to 4 here because this function isn't valid for x equals 4. But we can use this function to deal with our boundary conditions at the left end. Okay, so when x is equal to 0, V is equal to, everything in the parentheses goes away. We just end up with, this one goes away, we just end up with C2 is equal to 0. And so we can update this function. And we get V is equal to 1 over EI times the quantity RAY over 6 x cubed minus MA over 2 x squared plus C1x. And now we know that C2 is equal to 0, so that's gone. And then V prime is, we have an expression for it here. It's equal to 1 over EI times RAY over 2x squared minus MAX plus C1. when x is equal to 0, that's just equal to C1. And that has to be equal to 0, so update this function. And it says v as a function of x is equal to 1 over ei times the quantity ray over 6 x cubed minus ma over 2 x squared. So this gives the deflection for the region between 0 and 1. Any questions about that? Okay, so let's just finish this next time.